All right, so let's talk about something called the equilibrium constant. The equilibrium constant is the Kc. The Kc is a ratio of the concentration of products to the concentration of reactants at equilibrium. So what does that mean? Well, let's use the example that we used in the previous video of equilibrium, where I'll write the equation up here from the previous video, where we had hydrogen gas reacting with carbon monoxide gas, and it's in equilibrium with water vapor and carbon monoxide gas. So if I asked you to write the Kc of this equilibrium reaction, you're going to write the concentration of the products compared to the concentration of the reactants. So the way that we write this is we would say Kc equals the concentration of the products over the concentration of the reactants. And there are some rules here when writing the Kc. The first rule is that any coefficients become exponents when we're writing what's called an equilibrium expression. So this Kc is the equilibrium constant. This whole thing, the Kc equals the products over the reactants, is called the equilibrium expression. And I'll try to be clear about defining what I'm talking about in different situations. So when we're writing the equilibrium expression, any coefficients in your reaction would become exponents. Well, there's no coefficients here, so we're not going to see any examples in this particular situation, but we'll look at some other ones. Another rule is that the equilibrium expression excludes pure substances. For these purposes, pure substances are defined as solids or liquids. Pure substances do not contribute to equilibrium, so they are excluded from equilibrium expressions. Again, this problem contains all gases, so these are all going to be included in the equilibrium expression. We'll see some examples where we leave this out, and we'll use these rules. So let's write the Kc, the equilibrium expression for this reaction. So I'm going to say Kc equals the concentration of the products over the concentration of the reactants. So it's going to be the product of these concentrations, so multiplied together, over the product of these concentrations multiplied together. So I would say the concentration of water vapor, and you don't have to include the phases in the equilibrium expression, times the concentration of carbon monoxide over the concentration of hydrogen gas times the concentration of carbon dioxide gas. This is the equilibrium expression for this reaction. Again, we followed all the rules. Coefficients became exponents, so all of these have a coefficient of 1 that's not showing. All of these have a exponent of 1 that's not showing. It excludes any pure substances like solids and liquids, which we don't have any here. So this is the equilibrium expression. If we had actual values for these concentrations, we would plug it in. The number that we would get, the Kc, that would be the equilibrium constant. So we'll look at that again in a minute. Let's do another example of writing an equilibrium expression where we can apply some of these rules. So let's look at a different reaction. I'm just going to use kind of a generic one. So let's say here is a reaction. The little letters in front are going to be the coefficients. So then A, this is the coefficient, and then this would be the element or the compound. And then CC, this is a liquid, plus DD, which is a gas. So now if I was asked to write the equilibrium expression for this, I would say Kc equals the concentration of the products. Well, now here, this Cc, which is a liquid, is excluded because it is a pure substance. It's a liquid, so it's not going to be included in the equilibrium expression. Sometimes you'll see that these, instead of just being totally excluded, it's just replaced with a 1. I'll put that in there just so you can see. So here we'll just put 1 times the concentration of D. In this case, little d here was my coefficient, so it becomes my exponent. And then down here it would be A raised to the lowercase a times B raised to the lowercase b. So this would be the equilibrium expression, and Kc would be the value there. Let's look at one more example. Let's say I had this reaction. Let's say I have a reaction and it is 2 moles of carbon dioxide gas is in equilibrium with 2 moles of carbon monoxide gas plus oxygen gas. So if I asked you to write the Kc of this, you would say Kc equals the concentration of the products. So the first product is carbon monoxide. This has a coefficient of 2, which means it is squared, times the concentration of O2, oxygen gas, over the concentration of carbon dioxide, again squared because it had a coefficient of 2. So these are the rules for writing the equilibrium expression. Kc is the actual number that you would get when you plug these concentrations in. So let's do an example of solving for the Kc. So I'm going to use this example that we just did right here, and I'm going to write out the word problem. So the word problem says, at equilibrium, .00 moles of carbon dioxide is at equilibrium. 2.00 moles of carbon dioxide exists with 0.50 moles of carbon monoxide and 0.75 moles of oxygen. And we'll say all of this is happening in a 2.00 liter container. So we have a 2.00 liter container. In that 2 liter container, we have 2 moles of carbon dioxide, 0.5 moles of carbon monoxide, and 0.75 moles of oxygen gas. So one thing that's really important to take away from this is that it says at equilibrium, because the Kc is the ratio of products to reactants at equilibrium. So if we were not at equilibrium, we would not be able to write Kc for this reaction. So this is important. This tells you we're talking about the Kc because these are the concentrations at equilibrium. So what we're given in this problem is we're given a number of moles and we're given a volume. Remember, these are concentrations concentrations in molarity, because that square bracket indicates we're talking about molarities. So I'm just going to write out what we would do kind of in steps. So I'm going to say step 1, we would write the equilibrium expression. Step 2, we would solve for the molarities. And step 3, we would solve for the Kc. I guess I didn't even ask that in the question. At equilibrium, 2.00 moles of carbon dioxide exists with 0.5 moles of carbon monoxide and 0.75 moles of oxygen in a 2-liter container. What is the Kc, or the equilibrium constant? Okay, so first we're going to write the equilibrium expression. So the equilibrium expression we just did over here. It's the concentration of products over the concentration of reactants at equilibrium. 2, we are going to solve for the molarities. So we know that molarity, I'll do that over here, molarity equals moles per liter. So let's solve for the molarity of carbon dioxide. So we have 2.00 moles in 2.00 liters. Equals a molarity of 1.00 molar. So now let's do carbon monoxide. What is the molarity of carbon monoxide? Carbon monoxide, we have 0.50 moles in a 2.00 liter container. So that means I have a molarity of 0.25 molar. And then lastly, for oxygen, I have 0.75 moles in 2.00 liters, which means I have a concentration of 0.375 molar. So you want to pay attention to these questions, because when you're asked for KCs, you're using concentrations in molarity. These values were given to us as moles and then a volume in liters, so we needed to convert those moles and liters into molarities. Once we're there, now we can solve for the Kc. So I'm just going to plug this in, remembering to square the ones that had coefficients of 2. So I'm going to write this all out. I'm going to write Kc equals the concentration of carbon monoxide, which we said is 0.25 squared, times the concentration of oxygen, which we said was 0.375, over the concentration of the reactants, which is 1.00 molar, also squared because I had 2 moles of it. So now we're just going to plug this into the calculator. I'm going to say 0.25 squared times 0.375 divided by 1 squared is 0.0234375. Remembering to always pay attention to significant figures. So because this is a multiplication or division problem, the fewest number of significant figures in the problem is the number of significant figures that your answer should have. So this has 3, this has 2, 2, 3. So 2 is the fewest number of significant figures in my problem, so my answer should have 2 significant figures. So the equilibrium constant, Kc, is 0.023. This equilibrium constant is a ratio. It's a ratio. There are no units. No units for the Kc. It's just a ratio. It's a ratio of products to reactants at equilibrium. Remember, this number has 2 significant figures because leading zeros are never significant.